Students often ask and question if imaginary numbers are actually useful. We find that this question usually has quite little to do with the math itself, but more to do with that word imaginary. Compared to the word real numbers, the word imaginary creates a sense that it is fake. Perhaps it is not meaningful, and that it is not a real number, which is actually accurate. Imaginary numbers are not part of the real number system that we are used to working with. And that is exactly where the misunderstanding begins. To understand imaginary numbers properly, we first need to think about something more fundamental, and that is multiplication. Starting with any number and you multiply by 1, it represents the same quantity, no change. And if you multiply by a number that's greater than 1, the quantity increases. You move further away from 0 in a certain direction. On the other hand, if you multiply by -1, you reverse the direction. So if you multiply by -2, you can think of multiplying by -2 as two separate actions. First step is -1, where you reverse in direction, and step 2 would be multiply by 2, where you move further away from 0 in the opposite direction. So if you ignore the size of the number, ignore the absolute value, ignore the magnitude, and just focus on the numbers 1 and -1, we can say two things. Firstly, multiplying by 1 essentially does nothing, not very interesting. Multiplying by -1 is to reverse its direction geometrically. We can visualize that as a 180-degree turn. So therefore, it must be logical to say that -1 is 180, another -1, another 180, and in effect, there's a 360-degree turn, which brings us back to +1. And therefore, it must be logical to say that -1 multiplied to -1 is +1, and that is the meaning of a square, that -1 squared is +1. To say the same thing in the language of algebra is to consider this problem of x squared equals to 1, essentially asking what are all the numbers when squared gives +1. X equal to 1 is obvious. Multiplying by 1 does nothing. Multiplying by 1 again does nothing again, and therefore 1 squared must be 1. That's easy. We just established that -1 multiplied to -1 also gives +1, and therefore the solutions to this problem of x squared equal to 1, the two solutions, one of them being x equal to -1 and the other being x equals to +1. Now this raises a deeper question. If -1 multiplied to -1 gives us +1, -1 squared gives us +1, then should there be a similar action or number when multiplied to itself twice will lead us to the number -1? It is a simple question with a very obvious geometrical answer. If you want to do the same action twice to give you a total of 180-degree rotation, the simple answer is just do 90-degree twice. 90-degree twice will give you a total of 180 degrees. A very obvious geometrical answer, but not so obvious algebraic answer. Essentially, we're considering the problem of x squared equals to -1. Find all the numbers when squared gives -1. And we don't quite know how to make sense of it. +1 when squared gives +1. -1 when squared also gives +1. We don't quite know of a number when squared gives -1. Now, symbolically, we can just write down that one of the solutions is the square root of -1. It is something that when squared will become -1, even though we don't quite understand what that means. And then quite naturally, the other solution would be the negative of that square root, both of which will square to -1, at least symbolically. And our intuition about the geometry of this tells us that the square root of -1, representing 90 degrees, is probably something like this, and that the negative square root, negative implying in the opposite direction, that the negative square root of -1 is likely somewhere here. Now the problem is this: on the real number line, we could not find any number whose square gives us -1, and instead we found this object, the square root of -1, and the negative square root, both of which we do not think they lie on the real number line. And that is telling us that we found some numbers that are not quite real. And here we come to an important juncture. We basically have two choices. Number one is just to give up on the idea of a 90-degree turn and conclude that there is no number that can describe this action. Now, this feels so unsatisfying because the idea of a 90-degree turn is so simple, so natural, and so intuitive. It feels like something must exist to represent it. And when this idea is so compelling, instead of giving up in finding this number, we do something more interesting. We will expand the number system. So we imagine a new number which we conveniently called I. It owes its very poor reputation to its name, the imaginary number. It is a number whose square is -1. And sometimes we write I to be the square root of -1. It does create a little bit of confusion in algebra. So I is most accurately described as the number whose square is -1. So now we have two solutions to the problem of x squared equal to -1, one of which x equal to I, the number whose square is -1, the other being x equals to negative I multiplied to -I also gives us -1. And so we found it. We wanted a number which we can use to multiply twice to get -1. We wanted a number to represent halfway of 180 degrees rotation. We wanted a number to be 90 degrees rotation, and we found it. It's called I. So we realized that the real number line, having positive numbers on one side and negative numbers on the other, was quite good at describing forward movement and a backward movement, but that forward and backward movement was still quite one-dimensional. And that if we wanted our number systems to be able to describe rotation, now you cannot quite rotate in a one-dimensional system. Rotation is really a two-dimensional action. And I guess this gives justification to the existence of imaginary numbers, so the real numbers on the horizontal axis and the imaginary numbers on the vertical axis, and now our number system has become two-dimensional. So we can see that imaginary numbers have some meaning to it. At least they help us to reinforce that multiplication is a kind of transformation, and that there is geometry behind the algebra, and that numbers are not just mere quantities, but the numbers can represent movement, and in this case, rotation. And finally, back to the question of the value of imaginary numbers. Thankfully, imaginary numbers did not break our existing system of real numbers. They are not a replacement. They are just an extension. So in that sense, they are optional. Even if you remove all imaginary numbers, your everyday life will still work. Nothing will fall apart. But if you choose to accept imaginary numbers, then something interesting happens. You gain access to a wider system, a system that allows you to describe problems that were previously impossible to express. Your universe expands, at least mathematically, and in that expanded space, you start to see new structures which did not exist previously. You start to see a better connection between algebra and geometry, and that consistency, that coherence, to me feels almost artistic. And perhaps that is the real point, that it's not a question of if imaginary numbers are useful or not useful. but that math is not a static system, that it can expand to become larger than the one you started with. And in that larger space, there is room for logic, of course. But to me personally, in that space, there is art. And honestly, this is quite beautiful.